So yeah, as I was saying, basically the talk will be about audio redundancy in WebRTC, and more specifically, I'll of course touch Janus a bit because that's the WebRTC server I authored, I wrote, and that's where I'm experimenting with Red myself. So I'll spend a bit of words about this as well. And this is just a very quick slide about me. No real need for an introduction because David already gave it. But just to give you some pointers, there are some links there where you can get in touch with me or just check what I like to do as a hobby, these sort of things. And I am one of the main co-founders of Meetecho, which is a small company based in the south of Italy and specifically based here in the beautiful Naples. So our office is around here, more or less. So definitely not a bad place to be stuck in a pandemic. And as I was saying, I'm the main author of Janus, which is an open source WebRTC server. You can find there some pointers to where the repository is. We also have many demos that you can play with before you decide to install Janus if you want to give that a try. We also have an extensive documentation online and a very active community on that group that you see over there, where people exchange ideas and feedback every day to try and solve issues that they may encounter. And just to give you a very quick overview about Janus, because of course I won't delve too much into details about what Janus is, but this is just to give you a very quick overview. It's conceived as a modular architecture where basically you have a core that is responsible for the WebRTC termination, and then you have different plugins that can basically take care of different functionality that you may be interested in. So we have an SFU plugin to take care of features like web conferencing, e-learning, and stuff like this. We have a plugin for broadcasting, a plugin to take care of SIP, RTSP, and these sort of things. So basically, depending on which plugin you attach to, you can take advantage of different features dynamically. And this can also be, of course, combined at an application level so that you can combine features from different plugins using different media channels in order to create a more complex application than the individual plugin could take care of for you. And this modular approach basically helped us cover a wide range of different use cases. So, of course, we had a much narrower idea of how we wanted to use Janus when we first created it, and then people started becoming very creative with what's available in Janus instead. And so, basically, they started with more traditional use cases like traditional gatewaying, contact centers, conferencing, and these sort of things. And then they started moving to broadcasting, gaming, identity verification, even virtual reality, these sort of things, which was very exciting and is still very exciting for me as well. And the important point that I wanted to make, though, is that even though Janus is most of the times used for, especially for video, one way or the other, may it be for video conferencing, for broadcasting, or for something else, it's really not just about video, because there are many use cases where actually audio may still be, if not as important, even more important sometimes. And it's not just audio, of course, there's also data, live data, like data channels that can be relevant to a specific application. And actually, even recently, some applications just focus on audio. So they don't do any video at all, but are just interested in getting audio done right instead. And I'm really not even talking about, again, the traditional use cases like your contact center or call center, FPBX, or integrating with the legacy infrastructure, but even modern applications. And a simple example could be Clubhouse, which basically disrupted the WebRTC world a bit, because they basically focused exclusively on audio to do some sort of live podcasting functionality where you have a few people speaking and broadcasting to a lot of people in real time, and then inviting people in and these sort of things. Similarly, there are other applications that try to mimic a bit what Clubhouse was doing. An example is Twitter Spaces, which basically does the same thing, where you can create groups of people that talk together using audio streams, and then this audio becomes a broadcast that can be consumed by people interested in the conversation. And you didn't hear it from me, but actually Twitter is using Janus for parts of its of Twitter Spaces, over the Twitter Spaces functionality. And I'll spend just a couple of words of this later on this slide, but this is just to give you an idea. And of course, audio is not just limited to conversations, but also to more in general entertainment. So for instance, last year at FOSDEM, I made a presentation about how WebRTC could actually help musicians in the wild, especially during a problematic time like the pandemic, where again, WebRTC is typically used for conversational purposes, but music does play an important role as well. And music is indeed something that can be transported even in real time through WebRTC peer connections, whether it is for streaming a concert in real time or for doing music lessons or for doing a jam session together, these sort of things. So again, in this case, this is another set of use cases where audio is definitely much more important than video in this case. And in general, WebRTC, of course, has some functionality that are related to audio specifically. And when it comes to audio, there are specifically two different mandatory to implement codecs, which means that there are two codecs that all WebRTC implementations must implement to be called standard. One of those is, of course, G711, which was mostly added for making it easier to integrate with legacy infrastructure like PSTN or something like this. But most importantly, Opus, which is a high-quality codec that was specifically designed for the internet, unlike codecs that were quite widespread in the past also in VoIP, which means that it was conceived to be, for example, very flexible in terms of sampling rates, bit rates, and so on, while keeping the negotiation simple. So any change that may happen over the Opus bit stream is actually transparent to the negotiation, meaning that you can go from a 48 kilohertz to 8 kilohertz within the same session, and all endpoints are still able to deal with it with no problem at all. And most interestingly, Opus also have built-in support for stereo streams, and has different profiles when it comes to encoding for voice and music, which means that it can take different paths in the encoding process to optimize the output for one or the other, which again is very important because, as we said, there are use cases where conversations are important, and there are use cases where music is important as well. And stereo is a very good opportunity, of course, but there is also a little-known functionality that actually some browsers, Chrome specifically, also have an experimental support for surround audio as well, from 6 to 8 channel, more or less, called multi-opus, that is typically used because Chrome, the Google team needed it for Stadia, but can actually be used by other applications as well if you tweak the SDP a bit. And of course, there are several different tools that are of interest when you want to use audio and increase the experience. So for instance, you can take advantage of RTP extensions that notify you about voice activity detection, which means that you can detect voice activity without having to actually process the audio if the RTP extensions are set correctly. And a couple of ways to optimize traffic and reliability, like an in-band forward error correction support for Opus, which means that it's all done at the bitstream level of Opus if both endpoints are aware of it. And also this continuous transmission, which basically allows you to not send any traffic when you are actually sending silence, which may actually be quite helpful, especially in big conversations where you have a lot of data to be sent to a lot of participants at the same time. And so being able to cut on some data that is not strictly needed may actually help increase the performance a lot, because you reduce the throughput, you reduce the bandwidth usage and CPU usage as well, of course. Then it's also a matter of how should we handle audio? Should we handle it with an SFU or an MCU approach? And this is the usual debate. I actually made a presentation last year about how you don't really have to choose one or the other. You can actually use them both and take advantage of each other's strengths rather than be constrained by each other's weaknesses. And just in a nutshell, of course, you probably already know that SFU are typically ideal when you just want to relay media because you don't have any mixing or transcoding to do, so less CPU on the server. At the same time, you do require more bandwidth because it basically means that you have to relay multiple streams for as many participants as there are. When video is involved, you also have some more flexibility in terms of UI, because it means that you are not constrained by the mixed streams, but you can basically place the streams however you want. On the other hand, the MCUs are quite helpful whenever mixing media makes sense. And so it does mean some more CPU on the server side because you need to decode, mix, and transcode for each participant, and a bit of an additional delay because you do need to take some time in order to perform that. But on the flip side, you also can keep the bandwidth usage much more constant and consistent, which can be a great help in some use cases or for some specific devices. Which is why in the presentation that I mentioned, I explained that there are actually use cases where using both possibly for different aspects of your media application can make a lot of sense. And a very simple example could be, let's use an SFU approach for a conversation among a limited set of participants. The moment that we have that we have 1,000 viewers that are interested in a chat between 4 or 5 participants, why not mix those 4 or 5 participants instead and send a mix to broadcast instead, which means less data to relay to the 1,000 participants, but still allow the live participants to talk to each other using an SFU approach instead, which to my knowledge is, for instance, what both Clubhouse and Twitter Spaces typically do. So whenever they are actually broadcasting the audio to the audience, that stream is actually mixed while the conversation among participants is not. And it's also the mixed SFU and MCU approach is also what we use in our own virtual events platform. And more specifically, we use a mixed approach for audio while a relay approach for video. And even though when we actually need to broadcast a session that is taking place in an SFU mode in WebRTC, we can also mix everything and relay it with an MCU mode, for instance, to YouTube Live or Facebook Live or something like this, which means that, again, we can also combine SFUs and MCUs modes for both audio and video in different ways, which is why it makes a lot of sense to do that. But again, the main focus of the presentation is not really on audio in general, but on something specific. And so for audio in general, we've spent some time actually working on these in Janus, typically working on different aspects in order to try and improve the quality of experience of audio in the first place. And so, as I was mentioning initially, Janus does have a modular nature, which means that it's easier for us to then play a bit with the different functionality that we have to try and add functionality that is either specific to a custom plugin or a specific plugin. So, for instance, the Audio Bridge plugin may be the only one that benefits from some MCU features, or something that we implement in the core and can be taken advantage of by different browsers instead. And we started doing a lot of different things here, mostly coming from requirements from our own virtual event platform that I was mentioning before. So we had some things that we wanted to do there that couldn't be done with Janus out of the box. And so we said, why not try and enhance Janus in order to do that? And this was actually the main topic of a presentation that I made last summer at Open Source World, where I was a virtual guest. And there you can find a link to the slides if you want to learn a bit more about this. In this presentation, I'll focus more specifically on one of these functionality that we started working on, that is audio redundancy. And if you've been in VoIP long enough, you probably already know about RED in the first place. RED stands for Redundant Audio Data, and is actually a very old RFC. I think it's probably more than 20 or 15 years old for sure. I can't remember exactly. And so it's something that as a technology has existed for a very long time and was specifically written to provide some redundant functionality for audio streams in order to cope with packet loss and things like this. And so is in principle something that at least initially WebRTC didn't look at, mostly because WebRTC is inherently more, let's say, resilient and reliable in terms of transport, because it can take advantage of more recent technologies like NACs and other bandwidth control and things like this to try and cope with packet loss a bit more efficiently. But this is something that Chrome developers in particular started looking into in order to make sure that the audio quality could be enhanced even more, because even though audio of Opus FEC, forward error correction, can help, it doesn't always help as much as it could. And so basically the Chrome developers started experimenting with this a bit in order to see if this old technology could also be useful today. And so you can find there some pointers. And for the first link is the the ticket where they describe the implementation details and how the work is going on. And the other two instead are blog posts where other implementers started documenting their experience with RED and WebRTC in the first place. So in the first blog post, for instance, Philipp Hanke talked a bit how you could be enabled and it could be used, while in the other blog post, the Jitsi developers shared their experience in testing RED with WebRTC in a Jitsi video room, for instance. And so how it could be tweaked and whether or not it was actually providing any benefit. And basically, in a nutshell, RED provides you with a way to, instead of using an RTP packet to just send a single frame, you basically put multiple frames into a single RTP packet, including some audio frames that were from packets that you sent before, which means that if you miss some packets along the way, you can still use the redundant information from following packets to cope with the loss. So to make a simple example, this, in case you have a conversation like this where you have an audio stream going in one direction and one packet is lost, without RED, that packet number 8 is not available for decoding in any way. And so basically you could hear some losses in the conversation, some audio artifacts or something like this. With RED instead, what happens is that instead of just sending the current audio frame, you also send, within the same RTP packet, you also send the audio content of a couple of different frames, one or more, and that's something that I'll get back to later. You send one or more audio packets within the same RTP packet, which means that if, again, we miss RTP packet 8 because it's lost somewhere over the network, the recipient does have the content for packet number 8, for audio packet number 8, within the redundancy information of packet number 9. And so the audio decoder can still be fed with a consistent and a linear stream of audio data in order to use it properly. And negotiating RED is actually pretty easy. You just need to add a new RTP map and negotiate it as a different payload type. And then you specify which payload type you want RED to be associated with, mostly because, as we've said, as we've seen in this slide, in order to basically group multiple packets within a single RTP packet, you basically have to use a custom payload format within RTP, and that's basically what RED is all about. And so basically, sorry, let me shut this down. Basically, that's how you negotiated it. And so, for instance, if somebody offers RED, they may not pull it as the first payload type. If the other party accepts it, they may put it as the first payload type instead, which means, okay, let's use RED to exchange audio packets and let's do something with it. And that's what I eventually started experimenting with in Janus as well. So I wanted to add support for RED in Janus as well, which, of course, was a bit problematic, mostly because of the modular nature of Janus, which means that different plugins may handle the negotiation differently, and different plugins may handle media differently as well. And I'll spend a couple of words about this in a minute. And basically what I did was expanding the core functionality to add support for negotiating RED in the first place, and also some utilities to unpack and pack RED packets in the first place, so that if I receive a RED packet, I can basically come back to the original audio contents that are contained in the RED packet. And if I have multiple audio packets, create a single RED packet that contains all of them at the same time. So basically the primitives that would be needed in order to allow plugins to use the feature if they need it. And then I started basically integrating this functionality in different plugins to see how that worked. And basically, it was important, in my opinion, to support both endpoints that can do REDs and those who can't, which means that, especially in a scenario where we have a media server sitting in the middle, and so basically gatewaying the media between two different endpoints, you may end up in a situation where you have one endpoint that uses RED for its media and another endpoint that doesn't, which means that you need to be prepared for translating one to the other. So for unpacking RED and sending non-RED on the other end, and vice versa, which is why I started writing those utilities in the first place. And I started doing a basic integration in most plugins, except the audio bridge at the moment. And if you want to learn more, there is a pull request that is still in an experimental phase, but is already usable, at least in its initial stages. And I also wrote a a dedicated blog post which goes a bit more in detail than I could in this presentation if you want to learn a bit more. But just to give you a visual understanding of how that works, basically, when you have Janus in the middle, non-red to non-red is easy because that's exactly how Janus is working today. So you have RTP packets coming on one end. These are regular RTP packets, so they contain audio or video streams. We can just relay them on the other side without having to do any manipulation related to red in the first place. And also red to red is actually simple to do because all we have to do is basically just relay the red packets on the other side. If these user generated valid red packets, then this user will be able to unpack them and use the redundant information as needed. Red to non-red is a bit more complicated because, of course, the easiest way, and I'll get back to this in a minute, is to basically just pack the, when we receive a red packet and we have a non-red recipient on the other end, the easiest thing that we can do is just take the main data from each red packet and let's just relay that to the other participants, which is what we're doing right now, and is not exactly enough at the moment. And again, I'll explain this in a couple of slides. For the non-red to red, we can actually do a couple of different things. So on one side, we could just send the packets exactly as we receive them, which basically means no work at all for Janus, but also means that even if this endpoint supports red, we are not taking advantage of audio redundancy functionality, which means that, again, if a packet gets lost, they cannot basically recover that packet from the traffic that we send. Another option is to basically allow Janus to create a redundant layer ourselves out of the packets that we receive. So in case we receive 7, 8, 9, and so on here, we can basically create our own red packets out of all the packets that we receive in a sequence, so that these endpoint, even if they are experiencing issues, they are able to cope and basically take advantage of the redundant functionality in those packets when needed. And of course, I mean, as I mentioned, this is an initial integration, mostly because we haven't started a long time ago. And there are indeed some challenges that we need to address. So first of all, in the red to non-red case, we are not actually really taking into account the redundant information. And this is related to this to this slide over here. So in case, for instance, we are losing packet 8 from the redundant leg, in theory we could use the packet number 8 to actually send packet number 8 on the other end, but in practice we are just basically extracting the main data from the red packets at the moment in this initial integration, which means that if we lose packet 8, we will just send 7 and 9 to the non-red participants, which means that in practice, we are not really taking advantage of the redundant information when we have to basically use this redundant information ourselves, rather than just allowing endpoints to consume this redundant information. There's also the problem that the red packetization in Janus currently assumes in-order packets, which may not always be the case, especially when we're actually ingesting RTP traffic from external sources, which means that in this packetization that we are doing here, if we receive, instead of 789, we receive 798, the red traffic here may actually be a bit weird, and so something that should actually be taken into account sooner or later before we actually merge this in production. Then there is the problem that when used in plugins, the red packetization is currently shared whenever we are doing a one-to-many. So for instance, in SFU mode, like a video conference or something like this, if we are creating a red packetization ourselves for the content, we only do it once for all the recipients that are red compliant. And this is, of course, mostly for efficiency, because we don't want to do the same job over and over for all the people that are interested in this. But it may lead to some issues if, for instance, there are new subscribers that join and that immediately receive a red packet that contains redundant information for packet that they never received before. Which doesn't seem to be an issue in the test that we made, but it's definitely something that we need to take into account. And a similar issue may be when we're actually switching subscriptions in session, because in that case, the two sources may have different redundant information. And so when you are actually switching from one to the other, which is something that in Janus you can do on the same peer connection, they may be confused by the fact that they start receiving redundant information that is not related to the packets that they were actually receiving a moment before. So that's something that we'll need to look into. And this continuous transmission is also a potential problem, and that's actually a problem that the Chrome developers handled, and is related to the RED format itself, which is basically a problem that RED has a limited timestamp format for packets. And basically, I'm almost done. So basically, the impact on bandwidth is actually the main issue with RED in the first place, because the fact that you actually put multiple audio packets in the same packet means that you could actually start using a lot more bandwidth than usual for audio itself, which actually may steal some bitrate for the audio streams. And so Chrome initially started sending basically 2 different redundant packets along each new packet itself, which proved to be a bit more consuming in terms of bandwidth. And so they are now just sending 1 redundant packet along the packet they are sending right now, which reduces the reach of RED in the first place, but basically helps keeping the bandwidth usage compact, even though you can tweak that via some flags in Chrome if you want to test more. And that's basically it. I hope I managed to stay mostly on time. I don't know if there's time for any question. Thank you.
You were pretty much on time, Lorenzo. We're going to forgive you going over a couple of minutes because you're the last one before break. And also, your voice is so musical. It's a pleasure to listen to. In fact, during that presentation, I decided that I'm going to call you the Andrea Bocelli of the VoIP and RTC world. It's that musical. So thank you for that presentation. Let's give you a quick round of applause before we see if there's any questions. Okay, we don't have a question. We have a comment from Dave Horan, who's in the room online. He says, great job, Lorenzo. So some positive feedback. Any questions for Lorenzo from within the room? Not seeing any more. By the way, that was like a meta presentation, Lorenzo, because you referenced 2 or 3 other presentations that you've done before now and linked back to them, which was great.